here, and all those 12 days the bike is not available for my service. And again, this maintainability can be broadly classified into two things. One is scheduled or periodic maintenance, and another one is maintenance to unexpected failure. Now this is periodic maintenance, periodically doing it, periodically maintaining the system, and maintaining the system because of an unexpected failure, and this is not periodic. Examples are also there. Say for example, a printer is a typical example, which we can explain both what periodic maintenance and unexpected maintenance also. Now for example, the printer uses the cartridge. Say it is an inkjet printer, it uses the cartridge, and the cartridge needs to be replaced after n number of printouts are taken, because every cartridge, so there is a specification, you can print so many number of pages. Now after that, so you got to what, after this n, taking n number of printouts, you should go for maintaining, replacing the cartridge. And similarly, if the paper feeding part of the printer fails, this is unexpected, it's not going to happen all the time. So sometimes it might happen that time you require maintenance to unexpected failure, and this is not the periodic one. In both the maintenance, so whether it is a scheduled or periodic or unexpected one, now you got to bring the device to the offline mode. And when I say offline mode, because you got to repair it, so you got to repair only in the offline mode. When it is in the offline mode, it's not available for the user service. Now availability, so the availability of the system for the user service is given by this equation, and it is purely dependent on the mean time between failure and mean time to repair. If the mean time to repair the system increases, the availability also decreases. If I say the system, my bike goes down, and the garage people, the mechanic says, I need 1 month to repair your bike, then 1 month that is not available for my service. So similarly, and that is availability. Availability is equal to mean time between failure divided by mean time between failure plus MTTR, mean time to repair. So as now security is another important operational quality attribute of the embedded system, and security covers, as already mentioned, confidentiality, integrity, and availability. What is confidentiality? Protecting the data from unauthorized disclosure. If I say some data is confidential, so the data should not be displayed to or disclosed to the unauthorized users. And similarly, when I say integrity, even if the data is displayed, protection of the data and application from unauthorized modification. So let the user see the data, see my data, but they should not be allowed to modify my data. And availability deals with the protection of unauthorized users. Now I don't want my unauthorized user to enter the system. That is what is availability deal. Now examples are also there. Say for example, personal digital assistances. Now PDA can be a shared resource. Now that is many can use it, or an individual can also use it. Now if it is a shared one, so if many people are using the same personal digital assistances, then we should have something like username and password, just to prevent, achieve the confidentiality, because I don't want my data to be seen by the other person, then there should be a provision of username and password. And say and again also all the data and application present in the PDA need not be accessible to all users. Some of them are specifically accessible to administrator only. And again, you should have two things, two security level, administrator security level and user security level. And this is, I can say, the best example of the confidentiality. That means all the data which are related to administrator can only be seen by him, and they cannot be seen by the ordinary users. Now if I want to see the administrator data, then I have to log in as what with the administrative security credentials. Next, some data present in the PDA may be visible to all the users, but may not be necessary permissions to alter the data by the user. There may not be necessary permission to alter the data by the user. So this is an example for the integrity. Now okay, I'm using the PDA and I let the data visible to all of them, but I don't want the users to modify my data. I don't want the other users to modify my data. This is the example of what integrity. Let it be visible, but The system should not allow the other users to change my data. That is the example of, or modify my data. That is the example of integrity. So next is the safety. So as already told, don't confuse safety with the security. Sometimes they look confusing, but they are not the terms to be confused here. So security is different, which mainly deals with the confidentiality, integrity and availability, whereas safety mainly deals with the possible damages that can happen. So to the operators when the embedded system goes fail, or the damage that can happen to the public and the environment when the embedded system goes down. Now why it may cause the damage? Because the breakdown of the embedded system. If the embedded system fails, so that time it can cause threat to the human life or threat to the environment. Now our emission of a radioactive and hazardous material from the embedded products. So even this again leads to the threat to the operators and also to the physical environment. Now why the breakdown of an embedded system may occur? Because of the hardware failure or the firmware failure. So reasons are many, because of this, the embedded system, the possibility of an embedded system getting breakdown. Now and when safety analysis, as far the safety analysis is concerned, so when the engineers are building the product, so they got to anticipate all possible damages, and they should go for taking measures in order to minimize the effect of those damages on the human life and the physical surrounding. So they should take measures in order to control the damage to an acceptable level. So some safety threats are sudden, so some happens all of a sudden because say example the embedded system breakdown, and some happens gradually, say for example the toxic emissions from the product. So now till now you understood the operational quality attributes of the embedded system. So now from here we are understanding the non-operational quality attributes of the embedded system, testability and debuggability. Now testability deals with how easily you can test the embedded system. So testability of the embedded system, when I say testability, it applies for the both hardware and firmware. You got to test your hardware components as well, and you got to test the firmware also. Now when embedded hardware testing ensures that the peripheral and the total hardware functions in the desired manner, and whereas the firmware testing ensures that the firmware is functioning in the expected way, or as you require the firmware to function. And debug when you test the hardware components of the embedded system and the firmware of the embedded system, and if you feel like the system is not performing as required by you, then there is a problem with the embedded system. That means while implementing or designing it, you have got deviated. Now how to find the location from where you got deviated? That can be done only through debugging. So debugging is the means of debugging the product. So in order to figure out or find out the location or the place where the system is behaving unexpectedly, and you find that location and fix the bug, fix the defect. And again debuggability also applies for the hardware level debugging and the firmware level debugging. So debugging you got to debug the hardware. If there is an hardware fault, you got to debug the hardware, and if there is a firmware fault, you got to debug the firmware. Now evolvability, so and as already told, this is closely related to biology because I gave you the example of human evolution, and similarly the embedded systems are also evolving. So if I say evolvability refers to non-heritable variations. Say if I say the same variations are being inherited from the apes, we would not have been the humans like this, we would have been still like the apes. But there are certain features which are non irritable also. So an embedded system also uses this concept evolvability. That means when you're designing the embedded system, you have to design it in such a way that it is easy to modify and take advantage of the new technological changes. That is, it should be possible for you to add the new firmware and the hardware technologies when there is a significant change in the hardware or the software technology. Next is portability. This is what a system independence I had to say. That means surviving everywhere. Any place, if this embedded system is placed, it should be able to survive as it is without too many adoptions. Now that is what is the portability. Embedded product is said to be portable if the product is capable of functioning as such in various environment. As such as it is, if it is able to function in many different types of environment, then we say it is portable. That means I have the examples also. Say for example, porting refers to migration of the embedded. I'm talking here with respect to the embedded firmware. Now the embedded firmware which is written for one target processor, say Intel 86 processor, and if I'm able to port this successfully to another target processor which is say Cortex M3 processor, then I say it is portable. The firmware is portable, functions on this also and functions on this also. Now if the firmware is written in high-level languages, then it can be easily ported from one target processor to the another target processor. By doing minimum changes to the firmware. So for example, a little target processors, if when writing an embedded firmware, if I have used little processor specific function, and I can easily change this little processor specific function to the target processor functions easily, and I can recompile that program, and I can easily port it to the new target processor. Now if the firmware is written in string assembly language, then it becomes very difficult to port the firmware from one target processor to the other target processor. Now if the intention of, if portability is the major concern, then it is always preferred to write the firmware using the high-level programming language than compared to the assembly level programming language. If it is written in assembly level programming language, it is not at all possible for you to port from one target processor to the another target processor. If it is written using high-level programming languages with so little modification and adoption, you can make the firmware easily ported to other target processors also. Say for example, you might have seen the applications developed for the desktop systems. Certain applications developed using certain programming languages run only on the specific operating system, and this you might have experienced. And some applications run independently on any desktop operating system. I have an example to give. Say for example, an application which is developed using the Microsoft technologies like Microsoft Visual Studio. So these applications, they run only on the Microsoft platform, and they will not run on the other operating systems. Now, whereas the application which is written using the Java, which is from the Sun Microsystem, will run on any of the operating system that supports the Java virtual machine. Now time to prototype and market. Now what is time to prototype and market? It is time that is elapsed between the initial idea of the product or the conceptualization of the product and the product is ready for selling. That is what is time to product and market. The time that is elapsed between the concept of the idea of the product, and after you get the idea of the product and you'll be converting it into reality, that is the real product, and that is ready for selling. So the time between this ideation or the conceptualization and the product ready for selling, you call it as time to prototype and market. And usually a commercial embedded product market is highly competitive, and time to market the product is a critical factor in the success of commercial embedded products. So there may be yeah, and multiple vendors will also be there in the embedded industry. If there are multiple vendors, so if you come up with a new design and if you take too much of time in order to develop and market it, so the competitor of the product will take advantage of it and their product. So now in when I say the embedded industry, the time is very important. So from the time of conceptualization and this time of prototype market should be very less. Now you should, the moment you have the idea of the concept, it should be immediately within no time, in very less span of time, it should be converted into the reality or the product, and it should be ready for marketing. Now if you have the new idea and if you're taking more time to convert it into your product, since this is a competitive world, the competitor product may be available in similar type of product may be available in the market, and all your work will go waste. Now and one more important thing is, now in embedded systems, there is a rapid technological change that is happening. Now with respect to the embedded system, so every day there is a lot of technological changes happening, and if you start your design by making use of the new technology, and if you are taking more time in order to convert that into product, by the time your product comes into the market, the technology may get outdated and the new technology may come. That is the reason the time to prototype and market must be very less. Now what is a prototyping? Prototyping concept plays a major role in reducing this time between the prototype and market. A prototype is the basic model that is produced using the idea, and after you produce this prototype, you immediately expose it to the users, multiple users. Now get the feedback from the users and refine this prototype, and make it as a complete system. And prototyping is an informal kind of rapid product development, because this is the simple technique which you can use in order to quickly develop the software product, because you conceptualize the idea and immediately develop a prototype basic model using the main features, and after developing the basic model you expose it to the users comment. Now as and when you get the feedback from the customer, you keep updating your system or the product, and then when you have the complete knowledge on the system, you make the actual system and quickly deliver it to the market for marketing. So the time to prototype is another critical factor. If the prototype is developed faster, the actual estimated development time can be brought down significantly. In order to shorten the time to prototype, make use of all. Yeah, this is what you know. There is one more possible way to reduce the prototyping time, that is by using the commercially off-the-shelf systems, COTS. I think even in my earlier classes I told you COTS systems are available commercially off the shelf. The components which are available in the shelves of, say, as you go to the grocery shop, you will find the groceries available on the shelves, correct, right? And similarly, you go to any shop where the electronic components are available, reusable electronic components are available, get them and try to use it. With this you can reduce the prototype. Instead of developing all the components from the beginning, wherever you have the scope for using the reusable assets of the reusable components, try to reuse. Now per unit and total cost. So again this thing, per unit and total cost, will be monitored by both. One is the end user, that is the buyer of the product, and also by the product manufacturer. Both will be closely monitoring this, because this is a highly sensitive factor for commercial products. Now when the product is developed and it is ready for marketing, now you got to set a nominal rate. And if you're not setting the nominal rate for the product, so then there may be the failure of the product in the market. So because initially people won't buy the product if the cost is very high. Now what you have to do is, and slowly initially you got to have the price of the product as the nominal rate. Now product life cycle. This is one more important non uh, uh, non-operational quality attributes of the embedded system. Now, this is the product life cycle, which starts with the design and development phase. Now, first, when you want to build any product, it starts with the idea generation. So, the conceptualization. First, you should have the idea. After you have the idea, you should go for prototyping it. Just develop a basic model for it by using the important features, and then deliver it to the customers, expose it to the customers, get the feedback from the customers, and roadmap definition. You're refining your idea generation with the feedback what you get from the customers, and then go for actual product design development. So this is how you'll be doing. That is what is the product life cycle. First is idea generation, prototyping, getting concrete with the idea, and then by using the feedback given or supplied by the end users, and then finally go for actual product design. Now, and when you're doing all these things, there is only investment and no returns. Now, once the product is ready to sell and introduced to market, this stage is known as what product introduction stage. And during this stage, the revenue will be very low, because you will be setting the price to the nominal rate. Hence you cannot expect very high revenue during this stage, and gradually the revenue will increase with the time. And then when the product enters the maturity phase, that means when by the time you will get enough maturity in the manufacturing process, and you'll be knowing how to cut down the costs of the manufacturing process, and the slowly the sales growth also increases, and with the steady increase in what the revenue also reaches its peak. And after this maturity phase, and some point of time, over a period of time, so the product also reaches this stage called as product retirement or declining phase. Now, declining happens due to various reasons, like the competitors from the similar product, technology, because it may be because of the technological changes, and when the product enters into the declination phase, again the revenue starts decreasing, and the manufacturer, when it enters into the decline stage, the manufacturer announces the discontinuity of the product. So because they don't want to continue with the product, if they still want to continue with the product, they will they will have to face a loss. Just to prevent that, so when the product enters into the decline stage, so the manufacturer will announce the discontinuity of the product. And there is a graph in the next slide. This shows, so the x-axis you have the time, and y-axis is the revenue. When the product is under development, there is no revenue at all. You cannot expect any revenue. That is, this is only the investment phase and no returns. So product induction, that is the product introduction stage, this early stage, so the sales gradually increase or slowly increasing, and unit cost is, the cost of the product is fixed to this much. Now as the time increases, you can see the cost, the unit cost, the cost per product also decreasing. So any product you take, the cost of the product decreases over a period of time. So that is because of the maturity gained in the manufacturing process. Obviously the manufacturer will go for reducing the cost of the product. And you can see the product sales also increasing gradually. So growth, this is what is induction, and this is the growth stage, and this is the product maturity. Here the revenue reaches a stable state, and when the project enters into the retirement stage, the product sales also decreasing, and you have the profit also decreasing. You can expect the maximum profit between this growth stage and project maturity stage, and after that the profit is decreasing. Now here till here, now we completed the characteristics of the embedded system, and then you understood the quality attributes of the embedded system. And again, in quality attributes of the embedded system, two types: operational quality attributes of the embedded system and non-operational quality attributes of the embedded system. Now we'll stop here, and in the next class we'll start the continuation of this. Okay, thank you very much.